Okay, I think we should be going here. All right, so if you wanted to download like I said, those PDF is on there, on on the page. So details. So cladding. All right, we're starting this cladding section. We had done it last week. Um, this is really this is a very complex topic. You know, the technologies that are involved. You know, these are quite impressive, as to how this actually gets done on buildings. Uh, Not on everyone, but on some of those more memorable ones. Um, Now, because we're not together, because we are not um, in the classroom and hence can't walk outside, all right, what we would normally do on a day like today, we would go out and actually you're in class would have been an assignment where we go out and discover some building cladding systems on campus. And although we can do things virtually, take a tour, you can't really get that close, in terms of what what we would be attempting to look at. Um, so that's, you've probably done that before in other structures classes, gone on a field trip, the so-called campus field trip. So you probably would have done that like back in 226 or something like that, structural systems. So this would be a time that we would go do that. And so we are making the best of the fact that we cannot do that. Um, and so we will proceed as we can. And that's a little bit why we'll, do a little bit of time with project 3, to take the place of that. So building drift and cladding. Um, and there are a couple things that, just big picture, a lot of what you have been forced to look at, in this class is just the structural system of a building. And oftentimes we come up with pictures, frames. And of course, you would know that you don't often see a building that looks like that. Perhaps there's some bracing that's involved. Um, and so the pure structure, there's quite a bit of more work. It's not just a frame, it's not just sticks. Structurally, it's a good way to look at it, but there's an actual building involved. And as you would know, the building has a skin, right? Some sort of cover that's put on it. Now, again, you might be able to see the structure, parts of it, maybe quite a bit of it. But this cover, that the skin, the cover has to be held by the structure. And it needs to be held under, and I will go ahead and call them undesirable loads. When we say undesirable loads, we would be talking about wind, seismic, so much of what we talk about here with the issues, on cladding, we're going to talk about it in terms of lateral loads. The next slide you'll see here with, thermal expansion is an issue. That's not a seismic issue, but these sort of undesirable loads, have to be accounted for, and they don't always show up, and so, or they certainly are not there all the time. So we'll be using words today like in plane, and then also out of plane, motion, and compatibility or deformation. So we'll hear that quite a bit. Generally, the cladding is very stiff. And relatively speaking, the frame is flexible. So that's something that has to be dealt with successfully. So just kind of putting these functions of the cladding again in front of you, so I'm gonna let you read that. Sort of some primary functions. Um, it says adjust to wind or earthquakes. That's obviously subjective. I mean, when the earthquake is occurring, you might say that this becomes a primary function. Um, a primary function, but a lot of the things that we will talk about today is that, when these are occurring, that is, we want the structure to be separate. I'm kind of put that in quotes from the cladding. In a moment. All right, got somebody else there. So there would be the functions of our, generally speaking, what our cladding is going to be on the building. This talked about that last time, those 6 different ways that water can get into a building. So obviously it's extremely important when we get from the function of a building, the structure of a building, to then the actual function um, of the inhabitants inside the building. So let's kind of take a look at some cladding, kind of see down here, panel connection locations. And so let me just highlight these 2 here. The circles, right, would be tiebacks, and the triangles would be bearing. And so those triangles really are dealing with sort of gravity primary when something is bearing, and generally in the vertical direction, obviously. The tiebacks, and these tiebacks are going to really affect or hold the cladding in place due to in plane. It's going to sound like an engineering course here. Translation, right, and rotation. Perhaps back in your structures class, it spoke about translation, degrees of freedom, right? Translation and rotation. And so we're going to kind of break these up into in plane and out of plane. And that would be also translation and rotation. I'm going to go back just for a second here. So this would be the in plane, all right? Those in plane movements, and then the out of plane movements. So we could have long discussions about degrees of freedom, but I have a feeling that we would most likely not have created many fans out there, so we will stay away from that. So I'm going to color code this here. I'm going to do this in blue, the bearing. And so I'm just going to highlight these here real quick where those bearing points are. You can kind of think of these as if you were going to just hang a picture. It's not a perfect analogy because generally you wouldn't hang a picture at the bottom, because it would want to lean out, kind of rotate out. But you've got locations where you're going to support in a gravity, and then you've got multiple points. If you notice on all of these, there's more points that deal with the translation and rotation, right? The movement, as opposed to just the static. This is more of a static issue. Oops. And so you see you've got more of those points, and that's those increased number of points are what restrain more degrees of freedom. So again, we'd be right back into doing stability and instability. So you've got something that would be right there in a panel, right? The whole panel of a frame, something that would cover here, something covering a column on the exterior of a building, and then something that would be covering a spandrel. So if you were looking at a frame, so it would be something that would be sitting here, and then perhaps you would have glazing, some sort of glass above and below it. So that would be where that spandrel cover would come in. So we need to think about all these connection points. So that's what we're going to spend a little time looking at. So just kind of looking at these panel, and now just having you think here in terms of a building that has multiple panels, seeing where those floor lines possibly would be located, and then where those instability, and then where those connection points would be sitting, both the bearing and also the tieback connections. So again, these are the tieback, and then the triangles would be the gravity connection points. So we've got a picture here. This also, we're going to talk about this here in just a second, where those forces come from, right? Those seismic forces. And then those seismic forces get delivered by the supports. Right? And then also right here, that would be the mass times acceleration. So you've got, this is also known as the inertial force, and that inertial force is resisted by all the reactions that are occurring at all those different places. Here it would look like from a something that would have a column or a spandrel cover. So again, you've got a seismic load and a gravity load, right? That would both be present. Again, same thing here. You'd also have a gravity load that would be present, and then all of your reaction forces as well. So sometimes they would be occurring in the same direction. Sometimes they would be occurring in opposite directions. So both from the, right, this is dealing more with the translational degrees of freedom, and that's dealing with the rotational response. So cladding movement and the accommodations. So we're going to have different types of connections that we're going to be looking at. So we'll have sliding connections in light gauge frame systems, right, with a double channel, accommodations for vertical and lateral movement. We'll also have these with concrete panels. Push-pull connections, rods, you'll see that also with in the concrete precast panel systems as well. So just going back to those degrees of freedom, right? You've got sort of translational and rotational. This is more for in plane. And then this would be for both in and out of plane movement. Oops. Oh, no, not this again. Okay, so we'll look at a couple of precast panel connection failures. And so from a primary point of view, we've got, right, you've got a strong gravity connection down here, which would be very, right, it would be connected, something that would be embedded, and you've got something that pulls out here. So this would be a very rigid connection, very strong connection. And so we have a weak link that would be sitting there in our panel. So this is called cone pullout. And then a secondary effect could be that you end up with contact right there. So not only do you have primary damage, but also then secondary damage. Um, and from a yielded bracket, so not that you didn't have pullout, but you had some yielding that would occur, but this then creates out of plane, and then the same thing as the connections hitting each other, or the panel hitting the structure, um, and causing damage. So the way that the concept here, um, is, now we of course have a structural framing member. Give me 1 second here. Excuse me. All right, appreciate that. Thank you. So the primary structure. Then we've got some sort of an attachment. So this is like an idealized version here. Right, you got some sort of a connector body, which is going to work between 2 points of attachment. And then on the outside, you've got the cladding panel. And so some of the highlights here, is we want these separated, both physically, obviously. I don't like it when my pen does that. So we've got these things separated, right? And we talk about pounding, the way that there was that contact that occurred. But we've got something that here would be very stiff. Generally speaking, those are extremely stiff. And the structure is generally thought of as, at least from a relative point of view, it's going to be much more flexible. So this is where we've got a stiffness incompatibility. And so we can't make them the same stiffness. And so this is sort of like a fuse that's going to work between them. And so that connector body has design elements, um, either to remain elastic or allow movement, or becomes inelastic to then dissipate energy. But we don't want these two talking to each other. They want to stay separate. They're talking to each other through connection points, but we're trying to not have them talk to each other when we end up with seismic response. If there was no seismic or wind, then this would be a much easier topic to deal with. So I'm going to go here technical for just a little bit. I'm going to go kind of quickly here. This is more from an appreciation point of view. Now, earthquake loads, they occur it's a 3D problem. And so in plane, out of plane, in the vertical direction, those would just be the 3D movements. And so when we have an earthquake, the acceleration is in X, Y, and the Z direction. So that cladding wall is going to have loads in all those directions. And so the inertial force That's equal to mass times the acceleration, and there are 3 of those. If you want to think, really, there's 1, but it has 3 dimensions. So 3-dimensional problem. So kind of just from an appreciation point of view here, if we were to look at this panel and we see all the connection points, um, and we've got, this would be a sort of a weird view of this thing, but it would be like this. Oops. I don't know why it does that. I really So there would be at the center of gravity, there would be the weight. So this is a centroid. This is a statically equivalent load. Right? The weight is actually all distributed. So we've got this statically equivalent point load, and then that creates, right? That creates the reactions that would be from the bearing. So very simply, it's just like a beam analysis here. So here's like support, and there's the other support. So force and a force. So you could solve for those using statics. All right, vertical loading, this is mass times vertical acceleration. So whatever that vertical acceleration, that design, this is the design acceleration. So now you got a little bit more here, is that in that vertical direction, when we think of this panel now having an eccentricity to the actual wall, so the fact that this thing is connected to supports, it's sort of hanging out there. So there's going to be an eccentricity from where the support points occur. They're not actually right in the wall. So they are off the wall. So there's an eccentricity. You can kind of see how it is. Panel thickness over 2 plus offset plus bearing. So then in this case, right, it happens to be 200 millimeters. So it's very small distance, but there is an eccentricity. And so then you can solve for all of these forces over here by using statics. And so you kind of see you have to spin a moment, and you're able to find those reactions, both being 5.3 kilonewtons. So now we're starting to get in the out of plane direction here. So the in plane loading. So this would be in the, like, in that, from that first picture, like in the horizontal direction. So this again would be mass times acceleration is what would be occurring there. And so we've got now, right, reactions that we can solve for, right, both in the vertical direction, also in the horizontal direction. And the only thing we use, they've got 4 unknowns, but only 3 degrees of freedom. But we can say, due to the stiffness of the panel, we can say that in the horizontal direction, those forces are going to be equal to each other. The force is going to be equally distributed due to the rigid nature of the panel. And so each of those would be 74, right? 148 over 2. And then it just becomes, right, some statics on the structure. And then the very last would be the out of plane direction. And so this would also be horizontal, but this would be mass times acceleration, sort of in and out in the out of plane direction. And so what I've just really taken you through here is the fact that we've got, right, a nice amount of statics to then come up with our forces, our design forces. So you're not going to have to do this, but this whole thing of equilibrium really won't go away. It's just a concept we have to keep dealing with. And so this picture right here really brings out the fact that up here, right, we are restraining really only out of plane translation. Gosh, out of plane translation. Down here, we are restraining all three translations. So that's how we're holding this panel in place. That's how that panel won't, because we've got a panel that could translate and rotate. And so the fact that we have multiple connection points is what gives us the ability to restrain the rotation. So here's a little bit with some of the general concepts of detailing. I'm going to make that a little bigger. And so up, make this a little bigger. So generally down here, we'd have, this is where our fixed bearing points would be, right? Those are where the 3 degrees of freedom are going to be restrained. And then up here, we've got flexible movement connections at the top. And so that's where our sliding is going to be allowed to occur. And it's the out of plane directions, this direction, that is restrained by those flexible connectors. So those rods. Let me back up here. So here would be a picture of a sliding connection. Some of the characteristics of it. So just to, right, this is the cladding. All right, this would be the mains. All right, there would be a piece of the primary structure, right, a little slab. And so we've got here, we've got a sliding connection. So exactly what it looks like. And you'll see a better picture of it here in just a minute. Well, we've got some, right, freedom to move in that direction, right? We've got the flexibility. There is going to be some bending that's allowed. So we've got, it's very small, but it's not rigid in the up down direction, but it is in the axial direction. It's going to be the most stiff of all the degrees of freedom. So here's another kind of look at how those connectors would be created. And just to, right, highlight here, this is where the cladding is, right there. So sort of inside the building. So here's a look at some of the slotted connections and some of the connection points that would be allowed to, that would be created. So we'll talk about that here in just a minute. But you kind of get a look at, it says MCE, you can kind of read that. That's the maximum credible earthquake. So again, you want this thing to work such that that slot will allow for the drift that's going to occur when the biggest earthquake they expect, or from a design perspective, when that biggest earthquake occurs. You obviously sort of don't want to go 1 out of 10 on that. You would most definitely like to survive the largest earthquake. And again, we're looking even in those design documents. We're doing this from a life safety perspective. So we're trying to limit damage, but we're also trying to make sure that life safety occurs within the building. So a little bit of vertical construction tolerance needs to occur. So you can kind of see that that slot is a little bit wider than the bolt itself for some tolerance. And the washer itself right there has to be right thick enough because it essentially is going to be put in bending is what's going to occur with that washer. So that would just need to be insured. And there's a little bit here. I know these are in millimeters, but um, you can do the translation. Oops. As you can see, I got three more. So here's another look at the rod tieback, working from over here, the cladding, right, to the structure. So this high strength rod, obviously advantageous. So here it talks about the flexure of the rod. And if that is extremely long, right, or I mean, extremely, you have to just be aware of buckling, right? If we would expect a compressive load to be present, that compressive load would be because that cladding, right, would have an inertial force or a mass times acceleration. So there's another look at a bolted tieback. And then here, from a panel fixing point of view, the way that it's anchored, this is, we had looked at those about the pullout, just the cone pullout. And so one way to distribute the load is to have two anchor points and then to have a cast in recess, leaving you the ability for this thing to move a little bit freely without causing damage in the cladding. All right, so kind of wrapping this up, and then we'll take a little break. Um, so just from a philosophy point of view, right? Connection point, or the fixing, right, or the points of contact, and then in the middle was that fuse piece, just conceptually here. So it's like a chain link in that when one of the links break, then the entire chain breaks. So I know you've seen that analogy before, but you obviously don't want to have too brittle of a connection, then it's going to break. Having a ductile connection, but then you need to have strong enough fixings or connection points. And if you have strong connected to ductile, connected to strong, right? So this would be where the structure is. And then out here would be the cladding. So there would be the, right, what we're trying to achieve from a detailing philosophy point of view to make sure that this thing um, acts correctly. So if we were on campus, right, this would definitely be something where we would end up going on a field trip, finding some of these out sort of in real life. We'll do it today, but both today and Thursday, I'm going to start drawing and looking at more details, right, and the way that this detailing needs to occur. So that will be when we come back, we'll do that and then do the project. So it's 4:50. So I will give you and myself, let's do about 8 minutes, and let's see if we can hard start back at right before 5 o'clock. All right, we will start here on promptly. This will probably take, if I had to think, about 15 minutes, and then we'll end up with you guys in a couple of breakout rooms, and we'll see how if we can make some progress. We will make some progress on project 3. So I'm going to show you just 3 details. So we'll have more that we'll do on Thursday. I think timing wise, this works out. I've put these on the page on Canvas as well. So there's a separate uh, PDF. But here would be a picture, again, a detail of how these connection points would occur, would be looking like. So we've already seen this a little bit with the rod, with the slot. Um, and here would be the I-beam, right? So I've sort of hashed that. And let me just highlight here, we'd have a bracket, right? That bracket would then be welded in. And from it, that's where we would end up with welded connections here, right? Something that dowels into the, um, this is the gravity, sort of the bearing L. This is what's holding, right? That panel above. So this is the bottom of one of the panels. This would be the top. And then you've got a joint that would be, that would have an allowance here for relative movement, one to the other. So the size of that obviously depends on the size of the panels. How this then, from the bottom here, we've got a stiffener that's also put on, and then a brace that would be diagonal, that would be connected back to the rest of the structure. And that's what would end up holding that rod. This is one way that this would end up connecting. So this would be both bearing and lateral connection points. Also, the joint accommodates both vertical and lateral movement. And then we'll do 2 light gauge steel studs, if you will. So completely different here now. The finish on the building is not a precast panel. So got something that would be perhaps metal, something much lighter weight that would be occurring. And so then that slab would end up all the way out um, to where you're holding those steel studs, both connecting above. Below, we would have what's called a compensation panel. And this is what compensates or allows for the movement to occur, and that's the bottom, sort of the steel studs from below, and the steel studs from above. Then are sandwiching that slab um, that would be extending over the edge of the steel beam. So again, this is just an exterior, obviously an exterior. I mean, it could be a girder or a beam. Oh, delayed pen reaction right there. That's how you know it's time to think about wrapping it up here when the pen starts to go crazy. So that's one way that a light gauge system would be employed to hold a different type of finish on the building. And then the other one would be right here. Let me move back a little bit. This would be light gauge B, and now you've got where that slab now comes and sits right on the edge of the edge beam, and then light gauge clips would go out and connect to the steel studs. And we still have a compensation channel. It's just that the location of it is in quite a different spot. And so then on the outside, you still have the finish of your building. So this is obviously not something you would do if you're going to have a masonry finish that would be holding it, but if you had something that was going to be a lot more lightweight. So both of those would be options, and really it would just depend on the exterior system of the building, what would make you choose, what would why would the engineer choose one over the other? Really, it would just be from a connection point of view, and then also what the location of the compensation channels in terms of what the issues are with the finish on the exterior of the wall. So you'd obviously be able to have fewer of these than on that last one where you have to have one at each floor. This could actually be a multi-floor operation. So, all right, so there would be three of those details. All right, so now with our project three. So this is also on Canvas. This is going to be very similar. It's in a, this is basically like a project one and project two, but with a very interesting caveat here. I say it's not exactly, but it's similar. We're going to pretend no matter what building you choose, they're going to be your seismic coefficients in terms of calculating base shear. You're going to find a building that is between 80 and 150 feet. So basically, roughly a 10-story building, somewhere around there, 8 to 15 stories. Um, and this is something that you're going to find on the internet. This does not have to be at all a famous building. It could be one that you think is famous, or just one that you are a fan of. Would be fine, and you'll see exactly kind of what the caveat is here. Um, Inside that building, you can kind of read this. You're going to have two spaces that will require their own long span systems. So essentially, what you're going to be doing here is as if somebody's going to bring you. You're going to pretend like you are the engineer, and the architect brings, right, the sculpture to you. Call it a sculpture, and that's what they want it to look like on the outside at the end. And it is then up to you, in a sense, to how can you make it stand up. Now, this is, you've got some things on the inside of the building that you're going to be in charge of here in terms of creating a grid, right? You're going to have to design the slab beam, a typical, but you are also going to have to create a grid inside that beam, inside that um, structure. Make that a little bigger here. Um, and so you're going to design the gravity system, right? The lateral system. And so from the picture, which you're going to then have an idea of just what the size and what the cladding is. Now, we're not going to get into cladding on this project. And so that's what you're going to pick off of this. Of those long span, one, you're going to have to do one as a truss. The other one you'll do as open web steel joists. Um, and then also create, obviously, the lateral system, and choosing the lateral systems and doing all the design work on it. What the building is going to be used for is actually it's up to you, and I'll talk about that. I'll have an example here in just a second. You will also do a column design, and so you'll use that live load reduction. So really, it's just kind of you alone doing this, and like Jessica had asked, we will have consultations. So here's a little bit for the seismic coefficients, the R values, and you'll be doing pretty much the same, creating plans, and then obviously also adding in the lateral system elements. You'll show the framing, right? You'll show it, but you'll only have to do, right? You'll have to calculate a typical beam, girder, and slab. So you've got a little bit um, that you would be able to do. So I went and this would be my example. So as I was just perusing around, I mean, internet searching, and I found a 10-story building here. This is on the Auburn University, right? This is the library. And as you can see here, there's, you know, this whole complex, there's both a tower and, right, that part of the building, and then this sort of breezeway right there as well. So this would fit the, I also found this. There was a floor plan on there, but the floor plan really doesn't matter all that much. You know, you don't, uh, I mean, you can use that information if you'd like. You can make it slightly different. And so what I would do then with this project, so I've got something that's, you know, 10 stories or so. And I've got this other part of the building. And so I've kind of got 3 buildings. So I can kind of see I'm going to have some seismic separations. So I would most definitely be able to create perhaps a long span, something long span in that structure. Um, you know, if I wanted to, right? And this is where you've got quite a bit of creativity, right? If I wanted to actually, even if the building is not like that, but if I wanted to create a structure that had a courtyard, that maybe had a long span structure across it, or, you know, something like that, then I would be able to do that. I've got some creativity here, and what I could do at this point is this does not have to be exact, but I would then, right, I would be able to dimension this thing. So I would say, oh, that's 130 feet. You know, therefore the floors are 13 feet, or something, right? Something like that. Um, and then I would be able to also create dimensions. It doesn't, like I say, it doesn't have to be exact. You do not have to find the, you know, the actual floor plan of the building, but I would be able to have some elevations with dimensions just by sketch. So I'd have a big picture idea of what my building, or like I say, sort of here, it's a complex here, is gonna look like. So my pieces are sort of coming together now. The only caveat, the only thing that I cannot do is just copy the structural system and the lateral system that I see here. So I would need to. I'm gonna say that I want the outside of the building to look like this, but that doesn't mean that, you know, that's not a shear wall. Um, so that would just be exterior cladding that would be attached to the building. So I could say we could do this. I could do this in steel. I could create shear walls. I could make that a shear wall if I wanted to. Um, you know, I would have some creativity as to how I wanted to make the building stand up. So I need to not copy, but I would need the gravity system and lateral system. Okay. So again, I could do braced frames if I wanted to. Um, if I was doing this building, then I would, you know, I would most likely put those braced frames, right? So that I could end up with, right? I could end up with the picture that I see, um, and I just got to make that thing stand up. You can then create, and that's what I mean on in terms of when you end up doing your framing, you don't have to at all somehow, well, I need to know what the floor plan is so I can frame it. I can go in and at this point I can make my grid. I can just approximate if I see some grid, right? Some grid points, I can go in and just approximate that and put that on myself. So that's the scope of project 3. So you are going to be the engineer that um, assures that this sculpture the architect brings you, that's what you're going to make stand up. So I'm going to do this. I am just randomly going to do, let me stop this. All right, I'm going to stop the recording.